What if you lived on a neutron star? Welcome to the neutron star, one of the most extreme objects in our entire universe. Neutron stars are famous for their mind-boggling density, unimaginable gravity, and intense magnetic fields. Neutron stars are what physicists call stellar corpses, the dense remains of once massive stars. What is the point of a star if it can't even sustain fusion anymore? Thank you, Professor. No problem. Thank you. The professor does have a point. Scientists know a lot about neutron stars, but they're pretty unclear on what would happen if someone attempted to visit one. For one, neutron stars are so dense that a teaspoon of neutron star material would weigh about 10 million tons on Earth. That's as much as a small mountain. Do we know how that would affect a human visitor? Absolutely catastrophically. We should analyze what would happen if a human somehow managed to survive on a neutron star's surface. Let's explore that theoretical scenario today. What if you lived on a neutron star? First, we need to understand what a neutron star actually is. When massive stars run out of nuclear fuel, they explode in a spectacular supernova, ejecting most of their material into space. What remains is an incredibly dense core, a neutron star. Oh, see that tiny glowing sphere in space? It may look small, but don't let that fool you. A typical neutron star is only about 20 kilometers in diameter, roughly the size of a city, but contains 1.4 to 2.5 times the mass of our sun. To put that in perspective, our sun is 1.3 million times larger than Earth. Small size, massive matter, neutron stars have every extreme. What about temperature? Scorching temperatures, intense radiation. No more simplifications. Please. Crushing gravity. Neutron stars are born hot, incredibly hot. A newly formed neutron star has a temperature of over 100 billion degrees Celsius. That's about 6,000 times hotter than the core of our sun. While they cool over time, even an old neutron star maintains a surface temperature of around 600,000 degrees Celsius. By comparison, the surface of our sun is a mere 5,500 degrees Celsius. Oops, almost forgot. Let's continue. Thank you. And there's an even more spectacular aspect. A few years ago, scientists detected neutron stars colliding, producing gravitational waves and creating heavy elements like gold and platinum. These collisions are among the most energetic events in the universe since the Big Bang. Scientists are still studying the full implications. Fascinating discovery. Absolutely. The merger of two neutron stars releases more energy in a few seconds than our sun will emit in its entire 10 billion year lifetime. That's truly astounding. But let's get back to our hypothetical scenario. Living on a neutron star. The moment you approach a neutron star, you'd encounter its overwhelming gravitational field. That's right. The gravity at a neutron star's surface is approximately 200 billion times stronger than Earth's gravity. If you dropped a marshmallow from 1 meter above a neutron star, it would hit the surface at about 4.3 million kilometers per hour. On impact, it would release energy equivalent to a small nuclear bomb. Add this to our calculation database, please. Now, neutron stars also have extraordinary magnetic fields. The average neutron star has a magnetic field around 1 trillion times stronger than Earth's. Some, called magnetars, have fields even thousands of times stronger than that. Such powerful magnetic fields would instantly affect any electronic equipment. Your smartphone wouldn't just malfunction, its atoms would actually be distorted into cigar-like shapes aligned with the magnetic field lines. You always need to consider quantum effects near neutron stars. Indeed, at these extreme conditions, quantum physics dominates classical physics. The surface of a neutron star isn't made of anything we'd recognize. After the supernova explosion, gravitational pressure becomes so intense that electrons are forced into the atomic nuclei, combining with protons to form neutrons, hence the name neutron star. What remains is essentially a giant atomic nucleus about 20 kilometers across. The surface consists of a crystalline crust of iron nuclei, arranged in a lattice surrounded by a sea of electrons. This doesn't sound like a hospitable place. It's true. The surface of a neutron star overwhelms our everyday concepts of matter. The extreme gravity compresses atoms to unimaginable densities. The outer crust resembles a bizarre metal, but deeper layers contain nuclear pasta structures named for their resemblance to lasagna, spaghetti, and other pasta shapes as atomic nuclei are squashed and stretched. That was my favorite quantum pasta analogy so far. Alright, let's examine the rotation of neutron stars. When massive stars collapse, conservation of angular momentum causes them to spin extremely fast. Some neutron stars rotate hundreds of times per second. The fastest known neutron star spins at about 716 rotations per second. That means a point on its equator is moving at approximately 24% the speed of light. The incredible rotation, combined with a strong magnetic field, produces powerful beams of radiation that sweep across space like a lighthouse. When these beams point toward Earth, we detect them as regular pulses of radiation. That's why some neutron stars are called pulsars. What's remarkable is that these pulses are so regular, they were initially mistaken for signals from extraterrestrial civilizations. The first pulsar was actually named LGM-1, for Little Green Men. No, you are not suggesting actual aliens were involved. The name was just scientific humor acknowledging how regular and unnatural the signal seemed until their true nature was understood. But even this remarkable rotation is just one aspect of neutron stars' extreme nature. Their gravity is so intense that it significantly warps space-time around them. Near a neutron star, Einstein's general relativity becomes crucial to understanding what happens. You know, it's mind-boggling that the collapse of a massive star produces something as extreme as a neutron star. It really makes us think about the way that matter can exist in states completely foreign to our everyday experience. Indeed, neutron stars represent a state of matter that cannot be replicated in any laboratory on Earth. The closest we've come is in particle accelerators that momentarily create conditions somewhat similar to those in neutron stars. It's like that boundary between what we can study directly and what we can only observe from afar. Some phenomena are simply beyond our ability to recreate. Now let's consider what would happen if you somehow approached a neutron star. Long before reaching its surface, you'd encounter the extreme gravitational gradient. It's true. The gravity of a neutron star increases so dramatically as you get closer that if you were falling feet first, the gravitational pull on your feet would be significantly stronger than on your head. This differential would stretch your body into a long, thin strand of atoms, a process physicists call spaghettification. All right, let's say we develop some theoretical technology to shield against this effect. What would waiting for you on the surface be like? Check this out. Nuzzled neutron stars have a gravity so strong that it creates a significant gravitational time dilation effect. According to Einstein's theory of general relativity, time passes more slowly in stronger gravitational fields. 1 second on a neutron star's surface would correspond to about 1.4 seconds as observed from far away. Now, neutron stars don't have an atmosphere in the traditional sense. The extreme gravity pulls all gases tightly to the surface, creating a thin layer only a few micrometers thick. This atmosphere consists primarily of hydrogen, with traces of helium and carbon, and has a density comparable to steel. Beneath this bizarre atmosphere lies the outer crust, a crystalline lattice of atomic nuclei, primarily iron arranged in an exotic solid. Despite the extreme heat, the matter doesn't melt because the melting point increases with pressure, and the pressure here is beyond imagination. The surface of a neutron star isn't smooth at all. Some neutron stars experience starquakes minus sudden adjustments in their crust that release enormous energy. A major starquake on a magnetar can release enough energy to detect it from across the galaxy. The surface features of neutron stars are believed to include mountains, though not mountains as we know them. The strongest materials on Earth would be crushed flat by neutron star gravity, but the crystalline crust can support deformations up to about 5 millimeters high. That doesn't sound impressive, but maintaining even that slight elevation against such gravity requires incredible strength. Neutron star mountains also play a role in generating gravitational waves. As the star rotates, these tiny imperfections cause ripples in space-time that propagate outward at the speed of light. Beyond the surface, the interior of a neutron star becomes even more exotic. About 1 kilometer down, the nuclei start to merge, forming nuclear pasta meats, where atomic nuclei are squeezed into shapes resembling lasagna sheets, spaghetti strands, and other pasta-like configurations. Deeper still is the outer core, where matter exists as a superconducting superfluid soup of neutrons. This extraordinary state of matter has zero viscosity and flows without any friction. At the very center might be an inner core of even more exotic matter. Some theories propose that under such extreme pressure, neutrons break down into their constituent quarks, forming what physicists call quark matter or a quark gluon plasma. Now, if we somehow had a craft that could hover just above the surface of a neutron star, what would we observe? The visual appearance would be unlike anything in human experience. The intense gravity bends light rays significantly, creating a visual distortion of the surrounding universe. Stars behind the neutron star would appear to be in different positions or even form multiple images as their light bends around the neutron star. The neutron star itself would glow, but not like a normal star. Its thermal radiation would be primarily in the X-ray spectrum, invisible to human eyes. If we could see X-rays, the neutron star would appear as an almost perfectly round bluish-white disk. The surface features, minus those millimeter-high mountains, would be completely invisible at any reasonable distance. The neutron star would appear as a perfect sphere because gravity forces it into the most efficient shape, with any irregularities being insignificant compared to its size. If the neutron star is a pulsar, we might observe its radiation beams sweeping through space, though these would also be primarily in radio and X-ray wavelengths rather than visible light. One of the most stunning visual effects would involve the neutron star's gravitational lensing. The extreme warping of space-time means you could potentially see part of the far side of the neutron star, as light from it curves around to reach your eyes. This would create a distorted view, where more than 50% of the surface is visible simultaneously. The neutron star's rotation would create additional bizarre effects. Fast-rotating pulsars can spin hundreds of times per second, meaning the days on their surface last just milliseconds. This rapid rotation would create relativistic effects, with the apparent shape of the star becoming distorted due to its speed. If you brought a compass near a neutron star, it wouldn't just point in the wrong direction. The electromagnetic forces would rip it apart at the atomic level. The magnetic fields are so intense that they affect quantum processes, causing atoms to elongate in the direction of the field lines. These magnetic fields don't just distort matter. They're powerful enough to affect the behavior of light itself. Light passing through the magnetic field undergoes vacuum birefringence, minus the polarization of photons is altered by the extreme conditions of the magnetized vacuum itself. On a highly magnetized neutron star, or magnetar, conditions become even more extreme. The magnetic field is strong enough to make the vacuum itself birefringent, minus actually changing how light propagates through empty space. Chemical reactions near magnetars would proceed along paths impossible elsewhere in the universe. The magnetic field can make some ordinarily unstable atoms become stable, and stable atoms become unstable. Molecules would form in bizarre, elongated configurations aligned with the magnetic field. To put this in perspective, these magnetic fields are so intense that they affect the vacuum of space itself. According to quantum field theory, the vacuum isn't truly empty but filled with virtual particles that briefly pop in and out of existence. Near a magnetar, these virtual particles interact with the magnetic field in ways that change the fundamental properties of space. Even light behaves differently in such strong magnetic fields. Photons can split or merge, and the speed of light varies depending on its polarization and direction relative to the magnetic field lines. Another fascinating aspect of neutron stars is their perfect timing. Pulsars rotate with such incredible regularity that they're more accurate than atomic clocks over long periods. Their pulse rate predictably slows by tiny amounts over time, allowing for extremely precise measurements. This precision has practical applications. Scientists have proposed using pulsar timing as a galactic navigation system for future interstellar travel. By measuring the arrival times of pulses from several known pulsars, a spacecraft could determine its position in the galaxy with remarkable accuracy. Neutron stars also serve as natural laboratories for testing the laws of physics under extreme conditions. Their immense gravity provides opportunities to test Einstein's theory of general relativity in ways impossible elsewhere. One fascinating example involves the binary pulsar system PSRB, 1913+16, also known as the Hulse-Taylor binary. By observing this system over decades, scientists confirm that it's losing energy exactly as predicted by general relativity through the emission of gravitational waves. This provided indirect evidence for gravitational waves decades before they were directly detected. The extreme conditions inside neutron stars make them valuable for understanding nuclear physics. The densities in their cores exceed what can be achieved in particle accelerators, allowing theorists to test models of how matter behaves under such conditions. Another remarkable feature of neutron stars is their surprising cleanliness. Despite the chaos of their formation and supernova explosions, Neutron stars quickly become highly ordered systems. Their strong gravity sorts materials by density, with heavier elements sinking deeper, creating distinct layers. Neutron stars also exhibit superfluidity. Neutron stars matter with zero viscosity. This occurs because at extremely low temperatures, which still means hundreds of thousands of degrees for a neutron star, paired neutrons can enter a quantum state where they flow without any resistance. This superfluidity has observable effects. It's believed to be responsible for the glitches observers sometimes detect in pulsar rotation rates. These sudden speedups occur when the superfluid interior momentarily transfers angular momentum to the solid crust. Neutron stars eventually cool and slow their rotation over billions of years. As they cool, they become dimmer and harder to detect. The universe likely contains billions of these stellar fossils that have become too faint to observe from Earth. Some neutron stars have companion stars, from which they draw matter. These binary systems create accretion disks of material spiraling into the neutron star, heating to millions of degrees and emitting X-rays in the process. These are among the brightest X-ray sources in the sky. When matter falls onto a neutron star's surface, it releases enormous energy. A hydrogen atom falling from infinity to the surface would hit with approximately 200 MeV of energy, about 30 million times more energetic than a chemical reaction like burning hydrogen. This infalling material can build up on the surface until it triggers a thermonuclear explosion, an event called a Type I X-ray burst, which can briefly outshine everything else in an X-ray view of the galaxy. The smallest neutron stars are approximately 10 kilometers in radius, about the size of a city. The largest stable neutron stars are about 15 to 20 kilometers in radius. Beyond that size, they would collapse into black holes. This size limit is one of the great puzzles in astrophysics. Determining the exact equation of state that describes neutron star matter would help physicists understand the behavior of matter at nuclear densities. The study of neutron stars intersects with our search for dark matter. Some theories propose that neutron stars could capture dark matter particles. If these particles annihilate within the neutron star, they would produce detectable signals different from the star's normal emissions. Neutron stars also play a crucial role in the creation of heavy elements. When two neutron stars collide, they eject neutron-rich material that rapidly undergoes nuclear reactions, creating elements heavier than iron as including gold, platinum, and uranium. The 2017 detection of gravitational waves from such a collision, along with its electromagnetic counterpart, provided strong evidence that most of Earth's heavy elements originated in neutron star mergers. What's remarkable is that the gold in jewelry and the uranium in nuclear reactors likely came from neutron star collisions billions of years ago. In that sense, we carry a bit of neutron star history with us in our most valuable metals. So what if you lived on a neutron star? The answer, of course, is that you couldn't. Every aspect of a neutron star's environment is incompatible with life, as we understand it. The gravity, temperature, radiation, and exotic states of matter combine to create conditions that would destroy any known form of matter, let alone living organisms. But in contemplating this impossible scenario, we gain insight into the most extreme physics in our universe. Neutron stars push our understanding of matter, gravity, and the fundamental forces to their limits. These remnants of stellar death are natural laboratories for testing theories that can't be examined anywhere else. From Einstein's relativity to quantum chromodynamics, neutron stars challenge and refine our deepest physical theories. So while we could never visit a neutron star in person, by studying them from afar, we continue to unravel the most profound mysteries of how matter and energy behave at their extremes. In the grand cosmic perspective, neutron stars remind us that the universe contains realms far beyond human experience, places where the familiar rules break down and new physics emerges. They stand as monuments to how much more there is to discover about our extraordinary universe. That's the story of what would happen if you lived on a neutron star. A tale not of human exploration, but of the frontiers of physics itself.